We turn our attention now to equations. Essentially, equations are statements of equivalence, and the sign that we use to indicate that equivalence is the equal sign. Therefore, if children are going to understand equations, they must first understand the meaning of the equal sign. As adults, this seems like the kind of straightforward concept that we should be able to clarify in a lesson introduction, get it over with, and be done with it. Regrettably, it's not quite that easy. Children are first exposed to equations in kindergarten, and we expect them to be able to write accurate situation equations for themselves by the end of first grade. However, the equal sign has traditionally not received much or any particular instructional attention, and the end result are children who have very shallow notions about equations and the meaning of the equal sign. We'll be exploring those misconceptions and a couple of teaching tools for addressing them. And then in the following lesson, we'll explore the idea of facilitating children's efforts to write their own equations to represent a variety of situations and to use those equations to solve for unknowns. The research evidence indicating that children develop significant misconceptions about the equal sign informed the development of this Common Core standard. Not only do we know that the problem is prevalent in children, but further research evidence has shown that these early notions of the equal sign tend to persist throughout elementary school and lead to problems with subsequent study in algebra, even factoring in children's actual mathematical ability. So your work on this standard is really an opportunity to address these problems at their source, which is children's earliest exposure to writing equations. Children have a strong sense of equality in at least one sense. Since preschool days, they have known very well whether another child received more candy than they did, and they're ready to cry unfair at a moment's notice. So in working with concrete items, there does not really seem to be a problem with equality. But when we throw children into symbolic representations too early, their understanding of equality sometimes goes out the window. Equations are the symbolic language of mathematics, and we need to be very careful and systematic with this introduction. I'll give you an example illustrating how easy it is to lose meaning when thrust into symbolic language. At my sister-in-law's request, I did a math assessment on my twin nephews in late September of their first grade year. They had already received contact from the teacher indicating that she had serious concerns about one of the twins' math performance, although she said the other one was doing fine. So I began by looking at the math work that had come home, and it consisted primarily of practice sheets on basic facts, even in the first 2 weeks of the school year for first grade, solely in the form of equations without visuals. The nephew who was struggling had simply repeated the second addend for each sum. He consistently, for example, when faced with 4 plus 5, would say 4 plus 5 equals 5, because 5 was the second addend. That's not exactly an uncommon profile. Perhaps you've seen that. As part of the assessment interview, I gave him a verbal problem about 2 bags with 3 cookies in each bag. He immediately knew it was 6 cookies. He put 3 fingers up on one hand, 3 on the other, looked at them for a second and said, "Oh, it'd be 6. Clearly, he was making sense of the situation, even though he was failing the practice sheets. My other nephew, who the teacher said was doing fine in math, I gave him this problem. He immediately asked for a piece of paper and wrote 2 plus 3 equals 5 on his paper. Although he was doing fine by the standards of the practice sheets, he clearly was not understanding. Thrusting children into symbolic equations as a primary learning mode at the very beginning of first grade was a disservice to both of these boys, regardless of the grades that they were getting or their perceived success or lack of it on those practice sheets. It's easy to think about where we want children to end up, which is of course the abstract level, and to assume that if we merely give them enough practice at the abstract thing, then they'll get it. While practice does play an important role in mathematics education, practice alone, though, does not result in expertise. Rather, children need to gradually build their knowledge and skill base using what they've made sense of on a concrete level to build incrementally increasing levels of abstract knowledge. Along this learning journey, they need to make sense of how their concrete models relate to pictorial or diagram representations, and then how those pictorial models relate to abstract models like an equation. They need to be able to look at the abstract models, equations, and be able to put those back in concrete terms. Look at an equation and tell a story that matches. And even for some more complex equations, not just your classic 2 + 5 = blank. The most common misconceptions that young children develop about the equal sign is that it is a cue for them to compute the expression to the left of the equal sign, or a signal that here comes the answer now. Children who have this conception would have trouble with the equations that you see at the bottom of this slide. In fact, you sometimes encounter children who will tell you that you can't write equations that way. They might say things like, "What is that equal sign doing in the middle of that equation?" Or, "You can't write it that way. You have to write it 8 + 2 + 3 = 13. Unfortunately, these misconceptions are the seeds of big problems down the road unless they are addressed systematically in ways that guide children to deeper understandings of the equal sign. Much of algebra makes absolutely no sense if you view the equal sign as merely a signal to compute. Supposing we have a student who tells us one day that we can't write an equation with a total on the left, and we explain that in fact it is quite possible because the equal sign means that the expression on either side of it are equal or balanced, and since they're both equal or balanced, it's okay to write it that way. Have you taken care of the misconception? Not likely. One explanation doesn't typically do the job at all. This particular perception about the equal sign gets deeply ingrained in children. And as is the case with most deeply held misconceptions, it requires some cognitive dissonance and some ongoing experiences to shake loose that shallow perception. Additionally, teachers must consistently model correct usage of the equal sign and regularly express it verbally as a statement of equivalence. These are the same as, it's balanced with. We'll talk more about that teacher modeling component in the next lesson. Concrete tools can be used to support children's notion that the equal sign is a statement of equivalence. Here you see a balance that's used to measure weight and also a number math balance. These tools can be used to model equations and to illustrate that each expression is the same total, so they are in balance or the same as. For example, I could put 4 bears and then 4 more bears on one side and put 5 bears and 3 more bears on the other side, and it would balance, showing that 4 + 4 equals or is the same as 5 + 3. Sometimes I use an equals sign that is sticky on the back, and if we decide that the total's balanced, then I can put the equal sign in the middle of the balance, and then we have a concrete visual of an equation. 2 instructional tools have found measurable success in fostering cognitive dissonance and improving children's conception of the equal sign. The first of these instructional tools is even specifically stated in Common Core Standard 1.0A.7, and we're going to take a look at each of these similar and related approaches. Essentially, we can use a string of equations, one at a time, where they're not seeing the others. We just introduce them one at a time with time for dialogue. For the most effective use, the teacher tries to find alternative perspectives and uses that as a means of getting the children to think more deeply about the meaning. In other words, you actually want the kids not to agree 100%. You want to find somebody who's got a totally different idea than the others, because their disagreement, which can be respectful, becomes a source for a real need to know. We have to resolve this conflict in perspective. Okay, the first equation typically does not really involve much in the way of alternative perspectives, but for the second one, you might have someone saying it, some that say it's true and others say it's false. This is a great opportunity to get the different perspectives out there. Remember, the goal is not to give them the right answer, but to actually push their thinking, because the purpose is to get cognitive dissonance going. If you find that the whole class is in agreement on that second item and they all think that it's false, then you have a problem because they all have the wrong answer and there's no cognitive dissonance. In that situation, after eliciting to find out why do you think that can't be true, you can then tell them, well, I think a mathematician would say that it is true, because they would say that 8 is the same as 5 plus 3, and that's what the equal sign means. Now, are they all going to buy that? It gives them something to talk about. What do you think? Is that true, that 8 is the same as 5 plus 3? And then you can test that idea with a math balance. Then you have that idea out there so that when you get to some similar equations in other strings, some of the students are likely to be able to say, well, I don't know, because it is the same as, so maybe a mathematician would think it's right. So you start to just gently introduce. You don't assume that just because you said that, they all buy it, but you introduce an idea that some of the students might pick up on. You can proceed through the string accordingly then by having students give their reasoning and critiquing other students' reasoning. In the spirit of the mathematical standards of practice 2 and 3, you can get some really good dialogue here. The focus should primarily be on their reasoning, so don't rush to test it with a balance. But when the class appears to have given the different lines of reasoning that they have, and there's no real benefit in repeating the same reasons over and over, then you might shift to testing the equivalence with a tool such as a balance or a math rack to prove whether the two sides of the expression are the same as or balanced. In this way, you provide a metaphorical image of an equal sign as indicating an equivalence. Another instructional tool for promoting cognitive dissonance is the open number sentence. These are very similar to the true-false number sentences, but you see that there is a missing term, and the students need to figure out how to complete the equation so that it is true. This particular open number sentence that you see here is well known in the research literature. When children are not making sense of the equal sign, and when they do not recognize that equations are statements of equivalence, they will typically say that the number in the box should be 12 or 17. If they say 12, they are reading left to right, and they're acting on the misconception that that immediately following the equal sign, you're supposed to put the answer to what came before the equal sign. If they say 17, then they are operating under the assumption that you pull out all the numbers, look at what sign is there, and then do that computation and write it in the box. They're essentially ignoring that equal sign. So this approach allows you to see who has some of these misconceptions and who doesn't. And again, you can use the same approach where you try to foster dialogue and conflicting opinions, get students' reasoning out on the table, see if they can convince others in the class of the reason that they have. So you can use these open number sentences then to really pull out student reasoning and to use the alternative answers that they're producing as a tool to foster deeper thinking. Next, we're going to take a look at the extent to which the problematic perceptions of the equal sign exist, and also to what extent they persist over years of the curriculum. So if they have misconceptions at this early stage, do they get resolved before they get to algebra or not? We're going to take a look at that. And we're using, I told you that 8 plus 4 equals blank plus 5 that we just looked at. I told you it was well known in the research literature. We're going to actually look at the research data to determine how persistent and pervasive this particular misconception is. The first column actually illustrates the percentage of learners who accurately completed the open number sentence. So you might notice how extremely low the accuracy rate is. Most students chose incorrectly that either 12 or 17 was the correct response, with a few students saying, actually writing 12 in the box and then adding an equal sign and a 17 on the other end. That's the last column that you see. So the data indicates that the problem is pervasive, it is widespread, and that it persists across grade levels. In fact, one of the most disturbing aspects of this data is that the 6th grade children, who are on the very doorstep of having to do a lot of algebraic manipulation, did the worst of all on this particular task. So we need to be extremely thoughtful about the kinds of understandings children are getting about the equal sign at the beginning of their experience. This is an example of a center activity that can be used as a reinforcement to your number talks about the equal sign. Children have a target number and they're searching for as many equations they can write where the total value on each side of the equation is equivalent to that target number. So essentially they're brainstorming expressions that are equivalent, testing them on the number balance and recording them. The math balance proves to be an appropriate tool here as they work through equivalent expressions. And I should point out that expressions do not have to involve addition here. The number 8 is an expression if you're going by a mathematical definition. So you could have a whole number alone on one side of the equation. On either side of the equation, you can have 8 equals 8, for example. And you could test it on the balance and that would work. So that is an appropriate equation. So the students can spend time exploring and sharing their findings with the rest of the class. The instructional techniques we've discussed are clearly not one-off lesson ideas. You will want to revisit this idea regularly. If you do daily number talks, you might want to dedicate one number talk out of every 10 to 15 school days initially to ideas that relate to equations, true-false number sentences, or open number sentences. And then as the students are illustrating more awareness and understanding, you can revisit it occasionally. Certainly you should also, in your regular mathematical work with your lessons, be looking for evidence that there are misconceptions at work, or revisiting this idea as you talk with students and as they learn to write equations. If you're interested in doing some numbers talks on the equal sign, but you really wish you could see a video of children engaged with their teachers in these dialogues, then I strongly recommend the Carpenter book at the top, which I believe